So I've got a nice problem involving complex numbers today that uses a couple of different nice strategies. Our goal is to show for all natural numbers n that 1 plus 2i to the n is not a real number. So where I mean the square root of -1 for I. So this 1 plus 2i is a complex number. So showing that it's not a real number means that it must have a non-zero imaginary part when expanded out. Okay, so keeping that in mind, let's define two sequences. And we'll define those two sequences as the real and imaginary part of this expansion. So let's do that over here. So we're going to define, like I said, two sequences. I'll call them an and bn. They'll be sequences of integers such that we have 1 plus 2i to the n is equal to a sub n plus I times b sub n. So it's clear that those are sequences of integers because this is a so-called Gaussian integer, which is like a complex number version of an integer. And if you exponentiate this, you'll always get like integer terms for the real part and the complex part. But using this definition right here, we can in fact get not only seeds for these two sequences an and bn, but we can also build a recursion. So let's maybe first notice that a sub 1 is the number 1 and b sub 1 is the number 2. And that's because that's just 1 plus 2i to the first power. And now let's get our one-step recursion and we'll build that one-step recursion into a two-step recursion. So here we have an plus 1 plus I bn plus 1. So that's going to be 1 plus 2i to the n plus 1. But that's the same thing as 1 plus 2i times 1 plus 2i to the n. But let's recall that this 1 plus 2i to the n was defined over here. So that means we can replace that with 1 plus 2i times a sub n plus I times b sub n. And now we can multiply that out, gathering the real and imaginary parts. So the real part will be an, which we get from 1 times an, and then minus 2 times bn. And we get that from 2i times I. And then our imaginary part will be, let's see, 2an plus bn. So we've got 2an plus bn times I. So now reading off the real part right here, which is this, and then the imaginary part right here, which is this, we have this nice one-step recursion for an and bn. So we have an plus 1 equals an minus 2bn. And furthermore, we have bn plus 1 is equal to 2an plus bn. But let's recall that the real thing of interest here is the sequence bn. We in fact want to show that the sequence bn is never equal to 0. And if it's never equal to 0, then this guy is never a real number. So we don't really care so much about the sequence an, we only care about the sequence bn. But if you've got a linear one-step recursion like we do here for two sequences kind of intertwined, there's a trick where you can extend this out and build a two-step recursion for just one of them. In this case, we'll want to build a two-step recursion for the b sequence, like I said, because that deals with whether or not we have an imaginary part over here. Okay, so let's see how we can do that. So we've got bn plus 1 is 2an plus bn. Well, we can hang on to this bn term, but we'd really like to write this 2an term in terms of previous objects. So we can do that using the recursion up here, where we just replace n plus 1 with n. So let's see what that'll give us. This will give us 2, and then instead of an, we'll have an minus 1. And then let's see, minus 2 bn minus 1. So we have something that looks like that. And then plus this bn right here that comes down. So let's just maybe underline what's going on here. So this an term here has been used recursively or expanded recursively using our formula up here. And then this bn term is just coming down. So now let's maybe see if we can put some of this stuff together cleverly to get rid of the an term. Okay, I'm gonna rewrite this a little bit. Let's rewrite this as bn plus 1 equals, we will have, let's see, bn, I'll bring that out front, and then we'll have minus 4 bn minus 1. So minus 4 bn minus 1. So that's starting to look like our two-step recursion. But we have this correction term, which is plus 2an minus 1 that we need to take care of. So somehow we want to not exactly eliminate that, but rewrite that so it only contains b terms. But we can use this formula up here to do that exactly. So notice we have a 2an. That looks pretty similar to this 2an minus 1. So if we add a bn minus 1, we're good to go. So let's do that. So like I said, we'll add a bn minus 1. But if we add a bn minus 1, we also have to subtract a bn minus 1 so that nothing changes. Okay, now let's do some simplification. We have 2an minus 1 plus bn minus 1, so we can use that to write that as bn. So this whole thing right here is b sub n. And now we can combine that with the b sub n here, and we get b sub n plus 1 equals 2 times b sub n, and then minus 5 times bn minus 1. But now, in fact, we can finish this thing off very, very quickly. So let's reduce this thing mod 5. So this is going to be congruent to 2 bn mod 5. And that's because we have a multiple of 5 here. And so this is 0 mod 5. But that means bn plus 1 is congruent to 2bn mod 5. We have a one-step recursion. But now we can inductively work our way all the way back to b1 here. And what we'll see is that bn plus 1 is in fact congruent to 2 to the n plus 1 modulo 5. Okay. So what is that? That's from taking this line right here along with our seed over here and then just extending it all the way back. But notice that no power of 2 is ever a multiple of 5. So this is never congruent to 0 mod 5. So what do we have here? We've got a sequence of integers, bn, and none of them are multiples of 5. Well, what's a really special multiple of 5? The number 0. So if they're never a multiple of 5, then they're never equal to 0. But if none of these are ever equal to 0, that means that this guy right here always has non-zero imaginary part, which means this is never a real number. And that's a good place to stop.